Well, astronomers at the University of Washington are taking part in a new project called the Legacy Survey of Space and Time. It's a 10-year time lapse of the night sky from a telescope in Chile that UW helped get up and running last year. The Rubin Observatory will capture ultra-high-def images that could shed light on mysteries of the distant universe and our own solar system. It is being called the greatest cosmic movie ever made. I spoke with a UW professor who's leading that research. I'm joined by UW astronomy professor Željko Ivazić. Thank you so much for speaking with us. This landmark 10-year survey is now underway. What are you hoping to learn from this project?
There are hundreds of scientific themes that we will address with this new data. It's impossible to cover them all, but the two that stand out that captured people's attention is cosmological results on why the universe is accelerating. What do we need to assume to explain what we observed? And there are two ways: dark energy, and the other one is that Einstein's theory of gravity needs to be modified. This data will tell us which way to go between those two possibilities. And then on the other side of spectrum, close to home, we will be discovering millions of asteroids in our solar system, including those that may be on trajectories that might bring them to collision with Earth. We want to assure that there are no such asteroids, and we need to produce a very high-quality census and compute their orbits to convince ourselves that there are no such dangerous asteroids.
Rubin collects 10 terabytes of data every night. How are researchers sorting through all that information?
There are two steps in this process. So first, we need to reduce these images to calibrate them, to find objects and measure their properties. And that is done at the observatory level because that's something that everyone would do it. So it's more efficient if we do it once for all. From that point on, these results of measurements go to a giant database that all our collaborators can access. And then they can use their own tools to do specific type of science analysis they are interested in to produce scientific papers. The big new thing that we are providing with this observatory, with this data set LSST, is that you don't have to download your data to your computer because there is simply too much data, but instead you upload your analysis software to our database framework, and there you do your computations. There is simply too much data for everyone to download it to their home computer. You instead upload your tools, your software, with which you analyze your data.
It's incredible what you might have as far as technology 10 years from now when you're in the project as you do today. What can 10 years tell you full of data that 1 year can't?
So in astronomy, when we make an image, a picture, we are photon starved. So the reason why we make big telescopes and why we have very long exposures is to capture as many photons as we need to make precise measurements. So if you want to cover the whole sky to sensitivity level that we aim to because of scientific reasons, we need about 10 years of running the survey. Indeed, we had to build the whole new observatory that is 100 times faster in scanning the sky than any other existing observatory. What we will achieve in 10 years of scanning the sky with LSST, with any other large telescope, it would have taken 1,000 years. So we are super rapid. We are 100 times faster than any other telescope for scanning the sky. It's like getting a car that moves 6,000 miles per hour. It's truly transformative.
It is fascinating work. Thank you so much for sharing it with us, Professor. We appreciate it.